Okay, let's continue. B part 4, properties of the Hamiltonian. B part 4, lecture 11, Hamiltonian dynamics, intrinsic symplectic geometry. You see, that's important concept because Hamiltonian, in this case, is a bridge between the intrinsic geometry and this case, okay, and symplectic geometry. Symplectic geometry is related to the Hamiltonian, you see. So the intrinsic geometry is more wide, you see. So symplectic geometry is a particular case of intrinsic geometry. So let's I wrote here and I'll just read and comment. See, let's start. Hamiltonian dynamics is governed primarily by intrinsic symplectic geometry. You see, that's a relation between Hamiltonian and symplectic geometry. What is intrinsic geometry? Measured only using properties within a manifold, without reference to how it's embedded in any larger space. That is different from the, in this case, for the exterior geometry. Exterior geometry is what you see in general in advanced calculus, in physics and engineering. So intrinsic geometry is a special geometry which can be applied to all the advanced calculus. You see, that's important observation. Now, there's the symplectic geometry describe the phase space. Phase space is a cotangent space, the same as you saw previously in previous lectures. You see that a phase space is the same as a cotangent space. It's written here. You see T asterisk M. Now, the cotangent bundle, what is cotangent bundle? Okay? At each point of the manifold, you have a cotangent space. As exactly, you have the same, also the different tangent space. Tangent space is Tm. Cotangent space is denoted as T asterisk M. This consists of all pairs. You see QP. You see, when you write QP, you are just bringing the Hamiltonian. That's important here, you see. So the Q belongs to the manifold and P is a covector or dual space at Q. That is momentum MQI. You see, Q dot I. Q dot I are the velocity components, okay, of the generalized coordinates. So this space is automatically symplectic geometry. As I'm emphasized, symplectic geometry, the Hamiltonian, you see, is a tool of the Hamiltonian, which is related to intrinsic geometry. I think it's clear this. Now, observe that H is a function, okay, of Q of time, the generalized coordinates. These are the momenta, and T is there when you involve non-autonomous system. So then I can expand dH, you see, using this case the differential of H. Now look at here. As you showed before in previous lectures, dH is a vector. Okay, in the cotangent space. H is a scalar, okay, is form 0 DH is form 1. So this expanded DH. From the intrinsic geometry, the differential DH is also one form. Okay? It's a vector. So this I will advance what I'm saying here, just showing here. You see? So the tools of the cotangent space are in the study of exterior algebra. Okay? Then I will show to you the exterior algebra, which treat the tools of the intrinsic geometry. Now, then this is one form. DH is one form. On the phase space, in this case here, for non-autonomous system, then I add, in this case, the T, okay? Dependent, okay? Let's join here. Dependent, non-autonomous. In local coordinates, you see, you can see as a bundle of cotangent space bundle, and also in a specific local point. The specific local point, DH, is given by QI and PI. See, attention now. QI is in the denominator, okay? It means that I is downstairs index. You see, combined with the upstairs over here. Likewise, P, okay, is downstairs here, then goes is the same, okay, as upstairs. This DPI is downstairs, DQI is upstairs, and I is the dummy index. I is 1, 2, and so on, and you see it's important. This over here is 2n. You see, because you have 1 to n for QI and 1 to n to PI. So this space over here for the symplectic is even space. See? Now, we usually omit the T unless doing time dependent, where the space that's the note, but you see, this is cotangent space, okay, associated with the real, okay? The real is involved when time is involved. Now, dual basis and symplectic geometry. You see, what are the dual bases here? It's just dq and dp. You see, the canonical one forms is D acting on a scalar, in this case DH. You see, in general, by definition, the scalar is zero form. Okay. Now, and then for this case, the canonical one form for cotangent space, where DH is a linear combination of this base over here. Okay, this here is a specific basis. You see, this specific basis for the Hamiltonian. Okay? So, revisiting lecture 10, okay? In lecture 10, we solved trajectories belong to the cotangent space and using the symplectic geometry and intrinsic geometry. When I say symplectic geometry, is implicit, in this case, the intrinsic geometry. You see, intrinsic geometry does not imply necessarily symplectic, but the reverse is true. Symplectic geometry is associated to the intrinsic geometry. In symplectic geometry, this case, when Hamiltonian brings the symplectic geometry, so belongs to the symplectic. All this here, okay, in the literature, it seems a little confused. So that's why in this lecture 11, I'm emphasizing the difference between them. So, in this case, you see, lecture 10, the diagram are related to the trajectories belong to the cotangent of phase space. This is, I put over here, I remark the attention here, the tools of the cotangent space are in the study of exterior algebra. Exterior algebra, there, you see, you are going to open, okay, about the study of intrinsic geometry. You see, that's it. That's important here for you now to realize how important the Hamiltonian, symplectic, and intrinsic geometry. See, that's a main goal of this lecture.